Well, good morning and welcome. I'm Todd Gleason. I'll be your host for the morning. Welcome to this Conservation Cropping 2021 seminar this morning. We would like to thank our sponsors for the day. They include the Natural Resources Conservation Service from USDA, the the Champaign County Soil and Water Conservation District, the Illinois Environmental Protection Agency, the Illinois Stewardship Alliance, the Illinois Sustainable Ag Partnership, the American Farmland Trust, Sea Grant for Illinois and Indiana, University of Illinois Extension, Pro Harvest Seeds, and of course, the Illinois Department of Agriculture. Speaking of which, I'd like to kick off today by introducing you to the director of the Illinois Department of Agriculture. His name is Jerry Costello. He proudly serves the state. Agriculture, he says, has always played a key role in his life, and he was born and raised in Belleville, where he grew up visiting and working on his family's multi-generational farm in southern Illinois. Currently, he and his wife Lori reside in Smithton, only a short drive from his family farm, where he has 35 head of beef cattle. Good morning to you, Director. Thank you for being with us today.
Todd, it's absolutely my pleasure to be here. And I want to welcome you all to the 2021 Virtual Conservation Cropping Seminar. The motto of the seminar in conservation cropping, managing your inputs for healthy soils. This is the 8th year of the seminar. We're all going through interesting times, and it's the first time that the seminar has been virtual. Hopefully that actually gives an opportunity for the seminar to reach more people in this type of format. And this is the start of 3 great sessions that we hope you all will be involved in. The other sessions will be January 28th and February 4th. I want to let you know that the Department of Agriculture is reintroducing our Sustainable Ag Group. So we held the first meeting in several years last week. It's a 5-person panel, made up of farmers, mostly no-till and organic farmers. That is led by Gary Albers with the Department of Agriculture, located out of the Henry White Research Farm in Southern Illinois. The goal of this group is to make sure that we are creating a balance between environmental and economic concerns. One thing that I really am just super excited about, a program that we have at the Department of Agriculture, which has been an unbelievable success, is our Fall Cover for Spring Savings program. We're in the 2nd year of this program. And this year we had over 185,000 acres that were applied for the program. So the program will admit 50,000 acres, and we're still going through those requests right now. The program is closed for enrollment, but just to give you an idea of how successful this program has been, it took about 12 days in 2019 to fill up the 50,000 allotted for acres. This year, we filled those up, and as you can see by the 185,000 acres applied for, in less than 24 hours. So 2019, 12 days. This year, less than 24 hours. And what's amazing about this program, in 2019, 70% of the people who utilized it were actually first-time planters of cover crops. So it's an extremely, extremely successful program, one that, knock on wood, hopefully we'll be able to grow in the future. The department is also very proud to continue supporting the STAR program, which is Saving Tomorrow's Agriculture Resources. We applaud their success and just look forward to being in contact with them and participating as well. Many of you, and hopefully all of you, are also aware of the fact that anhydrous training at the agency is now online. So this is under a new state regulation, which is 8IAC 215. And anyone using or transporting anhydrous will have to complete this training. And it must be done by April 2022. And after that, you'll have to recertify every 3 years. If you would like to learn more about this training or actually complete the training itself, please go to the Department of Agriculture website. We are really, really looking forward to another year promoting innovative techniques of conservation in the state of Illinois and our country. So thank you all for being here and participating. We look forward to working with you in the future. And if there's anything that we can do to help in any way, shape, or form, do not hesitate to reach out. Thank you.
Thank you so much, Director Costello. We really appreciate you being with us for the day. It really helps the tone. And conservation, I know, sounds as if it's very, very important to you, as it is to those of us who work the land and those of us who help them work the land as well. We do appreciate you being here for the day. And thank you for helping us to kick this off. Now, I'd like to introduce to you a family of brothers that maybe you've seen from time to time on YouTube. These are the Peterson brothers, and they have a note for us today.
Hey everyone,
I'm Greg.
I'm Nathan.
And I'm Kendall.
Welcome to the Cover Cropping Systems Seminar. We hope you guys are excited for what you're about to learn and go through. We're going to give a little introduction to who we are and some of the things that we've done and why we're passionate about soil health and cover crops. We're three brothers that farm together in central Kansas, and we also make YouTube videos and different online content to promote agriculture, not only from an entertainment side of things, but also from an educational side of things. We got started back in 2012 with our first video, I'm Farming and I Grow It. And that video was a parody of a popular song that we took and changed the lyrics to and posted. And that video got 5 million views in a week. And we've since done 20 music videos about farming that we now have a combined view count on Facebook and YouTube of about 150 million views. If you'd have told us 8 years ago that that was even possible, we wouldn't have believed you. But we're really thankful for the exposure that those videos have brought farming and agriculture, and hopefully people have learned some from our videos as well.
We farm together as the 5th generation of our family farm, and it's a pretty typical Kansas farm. We grow cattle and wheat, corn, soybeans, grain sorghum or milo, and yes, lots of forages and cover crops. And so we're always looking to learn more about farming as well as show it to other people.
So we all three actually graduated from Kansas State University. Greg majored in Ag Communications, Nathan majored in Ag Technology Management, and I majored in Ag Econ. So we all three are kind of trying to take over different parts of the operation. There's a lot more people involved now than there was in 2012 when we first got started doing the videos. We actually were all three still in school then. So a lot of things have changed as Greg got married to his wife, Bricanna. Nathan got married to his wife, Riley, and I'm married to my wife, Kaylin. And our sister, who's currently in college, she helps out seasonally on the farm as well as our mom. And then our dad, and that rounds out the workforce here on Peterson Farm. And so we've learned a lot since 2012. Our farm has changed a lot, we hope in good ways. And with that, we've hopefully improved the soil and our livestock management, and pretty much every part of the farm we try to improve, and we have goals to hit those each year.
And Kendall just had a baby this past year, and then
Yep.
Nathan and Riley are expecting, and Bricanna and I are expecting. So lots of exciting changes coming to our family and our farm. And so just real quick, we wanted to talk a little bit about why we implement cover crops on our farm and why soil health is important to us. We have been a no-till farming operation since about the year 2000 is when we kind of got started with that. And our dad has always really believed in that system. And we farm in the hills of Kansas, or at least we think they're hills. And we think as far as the hills go, no-till is a great system. And then cover crops is kind of brings another layer of that to our operation. And so after making YouTube videos and having people ask questions about those, I think we all three have become a little more well-versed in kind of what all cover cropping and no-till and soil health entails. And we're going to perform a video at the end of our talk here that we actually made kind of dedicated to soil health. And so that explains a lot of my passion about soil health, having written those lyrics. But I think it's really important to be good stewards of the land and to keep soil from blowing or running off the field, and then it improves your bottom line as well.
Yeah, I actually minored in agronomy while I was at Kansas State, and so that was kind of where I first heard of cover crops and things like that, and it made me really excited because we have the cattle side and cropping side, and we do struggle with both erosion when we have too much rain and wind erosion when it's too dry, and then we are always having either too much rain or not enough. And if you do cover cropping right, it can be a challenge. Here we're usually short on rain rather than too much, but it can go either way. But it's a fun challenge to try to use cover crops to help balance out your moisture and save the water when you get too much of it, and conserve it for when it's dry. So that's what I like about them.
And there's a lot of different variables with our crop rotation here in Kansas, especially when we integrate both the cow-calf herd and grazing stocker cattle. And so in between, whether we're grazing crop residues or cover crops, there's a lot of value in getting livestock out on the land, and we can see that in the health of our soils. And we do testing before and after just to see organic matter, if we can raise that a full percent, and just getting the manure spread out on the field, there's benefit to that too. And so everything kind of works together in our operation, and then hopefully it makes the beef side more profitable and the cropping side more profitable.
Yeah, so we hope you guys have a great seminar, and we hope that this has been a good welcome message for you guys. We love talking about this kind of stuff, and we might even follow along with the seminar. But we're going to close our opening here with a parody song that we wrote and filmed that's called Residue, and it's a parody of Shape of You by Ed Sheeran. And so I hope you guys enjoy this. We're going to try to perform it down here with a phone speaker setup, and so I hope you guys can hear all right, and hope you enjoy. The city isn't the best place for me to be, and so the field is where I go. Me and my family on the farm, planting crops, working fast, and then we plant slow. And some of the farmers work the soil till it's bare, but trust me, give this a chance. Now take a ride out to our farm that we're surveying right before we start to plant. Now I'm singing like, soil, I know you need good health. That's why I take the soil test to the lab. Come on now, what do you need? S-C-A-N-G.
Say soil, got to protect you from all the rain, wind, and compaction too. That is why I love these roots. That is why I love these roots.
I'm in love with the residue that I pull my planter through. Although tilling is kind of fun too, I'm in love with the cover. Last night I was in the field, planting clover and radishes too. Every day discovering something brand new. I'm in love with the cover. Oh why, oh why, oh why, oh why. I'm in love with the cover. Oh why, oh why, oh why, oh why. I'm in love with the cover. Oh why, oh why, oh why, oh why. I'm in love with the cover. Every day discovering something brand new. I'm in love with the residue. One weekend we let the story begin. It sprouted and there's a big rain. Residues, it keeps the soil from shifting off the field like a runaway train. It's hot for hours and hours, but we don't even have to scour, cause our moisture is doing okay. When harvest comes from accident, it's far less taxing than working up the soil all day. Now I'm singing like,
soil, I know you need good health. That's why I keep the soil structure intact. Come on now, what do you need? Aggregates and microbe activity.
Say soil, got to protect you from all the rain, wind, and compaction too. That is why I love these roots. That is why I love these roots.
I'm in love with the residue that I pull my cedar through. Although tilling is kind of fun too, I'm in love with the cover. Last night I was in the field, planting clover and radishes too. Every day discovering something brand new. I'm in love with the cover. Oh why, oh why, oh why, oh why. I'm in love with the cover. Oh why, oh why, oh why, oh why. I'm in love with the cover. Oh why, oh why, oh why, oh why. I'm in love with the cover. Every day discovering something brand new. I'm in love with the residue. Enjoy the conference, everyone.
Oh, thank you so much to the Peterson brothers. We really appreciate that they managed to put that together for us. It was a fantastic way to kick off something I think probably all of us have been working for a very long time. Personally, I've been involved in conservation in one way or other about the time that I started at the University of Illinois, or was headed that way. In fact, I grew up in Logan County, which is just to the north of the state capital here in Illinois, and only about 20 miles from the Illinois Department of Agriculture, and was involved in the T by 2000 program in 1982 as an intern there. And of course, I'm involved in conservation today. No-till on the farm that my four older brothers farm there in Logan County, Menard as well. And also involved in the STAR program. By the way, there is a link to that STAR program you'll find if you want to know more about it already in your chat. Now, let's talk a little bit about the magic of soil. Nick Jelinski is here. He's an assistant professor of soil science in the Department of Soil and Water and Climate at the University of Minnesota, where he teaches basic soil science, field study of soils, and soils judging. His research interests are soil formation, enhancing access to soil information, and improving teaching and outreach for soil science and higher education and the general public. Nick has lived and worked around the world in soils and land management for state and federal agencies, as well as the private sector. Nick, thank you so much for being here today. The floor is now yours.
Thank you so much, Todd. I really appreciate it. And thank you, everybody, the organizers, for inviting me to be here. I'm going to switch my view for a second. As Todd said, I teach soil science. Soil is my passion. And I hope to kind of go through and give you a brief survey of the full scope of the incredible substance that we call soil. Far from just being dirt, soils are more physically complex, chemically reactive, biologically active than we can imagine. And our management of soil directly impacts human and environmental health. So I am a pedologist. I spend most of my life looking at soils in profile. And when I look at soils in profile, what I see is this incredible diversity of the substances that we call soil. These are just some soils from around the world. They're soils from Rhode Island, Alaska, Tennessee, Western Kenya, Nebraska. I've got the state soil of North Carolina. I've got the drummer in my presentation at one point because I didn't want to ignore the fantastic state soil of Illinois, and Sweden and Kentucky. And you can just see that, you know, most of us kind of look at soil from the top down and really only ever see the top 6 inches of soil or so. What I do in my life is study the full suite of soil properties and how they vary across time and space. And I think when you look at soil in this way, it becomes this really amazing thing. And I want to kind of highlight some of the main concepts that not only I teach my class, but that I think are important, have become really important for me in the research that I do. So very briefly, I am an exploratory pedologist. So a pedologist means I study how soil forms and why it looks the way that it does. So why do all these soils look very different? By the way, this is the drummer. This is your state soil of Illinois. I took that on the UIUC campus with Dr. Kevin McSweeney. And the exploratory part means I go to places where we don't have good soil information and try to fill in the gap, understand more about the soils of those places so we can make better soil maps. And the reason that soil maps are important, as I'm sure all of you know, is that that is one way to make soil information useful to people. Understanding variability across the landscape means that we can change management schemes in different parts of the landscape. We can tailor management for soil properties and not just treat soil as one homogeneous entity. A few things about my philosophy, and I truly mean this. It sounds corny, but it is absolutely true. Soils are magic. So actually, I'm producing a podcast for my basic soils class over the last year or so because we've been remote. And one of the episodes that we're going to produce this spring is called Stars to Soil. So the amazing thing about this substance that we call soil is that really the elements that form our soils came from the stars. And so we have this fantastic, amazing origin story of the soil materials that we interact with. And soils are the most complex environments on Earth. They're the only place where the hydrosphere, water, the lithosphere, rocks, the biosphere, life, plants, microbes, animals, and the atmosphere, our gases that make up the air that we breathe, interact. It's literally the only environment on Earth where those four things come together, and that makes them these really complex, amazing environments. Soils are connectors. I love this quote from Wendell Berry. The soil is the great connector of our lives, the source and destination of all. So it's true in a physical sense. It's also true in a cultural sense. Soil and the earth is a way that we can connect to each other and to the land. Part of that connection is that studying soil is really about studying ourselves. So Francis Hole was a famous soil scientist at the University of Wisconsin, and he liked to say that they were all temporarily not soil. And the reason that he said that is because basically all of the dry mass of human kind of tissues, all of our physical being, either comes directly from the soil or was supported by soil on its way into us. And the transfer of these elements from the soil to our physical bodies is mediated by the plants and animals that we consume. So there's a whole host of essential elements in us that come actually directly from soil minerals. So all the essential elements that don't have a gaseous phase, I've got some highlighted here, sodium, potassium, phosphorus, zinc, selenium, iodine, et cetera, all of these elements don't have a gaseous phase, which means that they are taken up by plants from the soil. And so their original origin, their point of origin before they got into the plants and animals that we consumed was the soil. And if we could draw lines from our body, if we could take every atom in our body, say every atom of magnesium in our body, and draw a line out into the world, we would end up with a line that arcs like a rainbow and points down to a soil somewhere in the world where that atom was taken up by a plant that was then processed and we then consumed. So there's a whole host of elements that come directly from soil. There's other elements that come not from the soil minerals, but the soil organic matter. And these have a minor gaseous phase. So elements like sulfur and chlorine, there is a gaseous phase in their cycling in the terrestrial biosphere. And that actually then makes it into soil organic matter through biotic activities. And then again, can be consumed, taken up by plants and consumed by us. Other elements come from air, but are supported by soil on their journey into our body. So particularly carbon and nitrogen. Carbon is brought down into the terrestrial biosphere from the atmosphere through photosynthesis. So plants are transferring carbon from the atmosphere to their tissues, which then become either part of the soil organic matter or are directly consumed by us. Same with nitrogen. So nitrogen, of course, is brought in by nitrogen fixation, microbial nitrogen fixation. Same thing, we're adding that nitrogen to the soil and consuming it eventually as it becomes part of our physical bodies. And then two other elements, oxygen and hydrogen, come from both air and water, but are supported by soil on their way through photosynthesis and activities by plants. So the bottom line is that we can trace all of the atomic building blocks of our body to soil or things that are supported by soil before they get into us. And so to study soil is really to study ourselves. And I want to highlight this in a very specific way. I call this the soil-heart connection. through potassium. I'm just highlighting one element here, but we could do this with all of the elements that I just talked about. So, you know, on a global average, there's about 1 to 2% total potassium in most soils by weight. And that potassium is largely contained in layered soil minerals. I've got an example of a mica here, which is one primary mineral that we might find in soils. And that potassium is actually contained in the layers. It's tightly bound in the layers of these soil minerals, and it's released slowly through weathering. By the way, there's another mineral called illite, which is actually named after Illinois, because that was the place where it was a first kind of, the structure was first described out of a deposit in Illinois, but it's very similar to mica. So a lot of the potassium in our soils is actually tightly bound in these layers of soil minerals. And this is kind of cool. On the right-hand side, I've got an example of a mica being weathered in the lab. And what's happening here, you can see this would be a fresh, unweathered mica in the top left. And you can see how it's got these parallel lines. As water and acids act on this, this was done in the lab, so it's much faster, but in the real world, you know, we're talking thousands of years, maybe hundreds to thousands of years, maybe tens of thousands of years. As the water and acids are acting on this mineral, they are slowly opening up these layers. And when they open up the layers, the potassium is being released out into the soil solution. You can see that if this is a fresh mica in the top left, on the bottom right is an example of a highly weathered mica. You see all the layers opened almost like a tattered book. And as those layers have opened, the potassium has been released into the soil water. Once released from the soil minerals and once the potassium enters the water, it's actually entering the water as a K+ cation, a potassium ion. That potassium ion can be taken up by plant roots and then incorporated into the plant structure. So I've got an example here of a banana, just because we always think about bananas when we think about potassium, but of course, every plant is taking up potassium. All the plants that we consume would be also taking up potassium. But when we consume those plant parts, the potassium becomes part of our body mass. So the potassium in our bodies came from those micas and illites in the soil, and that potassium actually makes our heart beat. So every heartbeat is really controlled by the movement of ions through selective channels in our heart. Potassium is one of the major ions that contributes to that electrical pulse that's happening as the potassium ions move through those channels. So just in a really crazy way, every heartbeat that we have is actually due to an atom that was contained in soil that was released through weathering over a long time scale and eventually made its way into our bodies. And if that doesn't blow your mind, get off social media for a while and put your hand in some dirt, because it's absolutely amazing. And it just goes to show how connected we truly are. So there's a lot of elements that are parts of our body that come from soils, either soil minerals or soil organic matter. That includes trace elements in our body. And that's why I say to study soil is to study ourselves. I also want to make the point that not only through physical connection are we connected to this amazing substance that we call soil, but also cultural and linguistic connection. So the human soil connection in linguistics is very strong, particularly in our English language, and the words that we use in our English language that are derived from a root in a language that we don't know anything about, but it would have been an ancient language, a root of a lot of the modern languages, Proto-Indo-European, that's that PIE acronym. The root of the term for earth is actually the main piece of a lot of our words that contain the root hume. So in Latin, humus, which we now use in English to mean kind of like soil organic matter, but the root in Latin actually kind of is better translated as earth or ground. So humus is earth or ground. Human, a bipedal primate mammal, that's us. Humanity and humility, those words all come from the same root, and the root is earth. So we have this very strong connection culturally, linguistically with soil, in addition to our physical connection. And what I want to impress on you in the next, now I'm going to shift to some more maybe science pieces of this, but basically soils are more physically complex, chemically reactive, biologically active, and diverse than we can ever imagine. And our management of soil impacts human and environmental health. Here's another image. Now I have a wider image of the drummer, which is a beautiful soil. And this was taken on the UIUC campus a couple years ago. So I'm going to start with physical complexity. Soils are more physically complex than we can imagine. This is also the drummer. And, you know, we talk a lot, particularly in soil health, we talk a lot about soil structure in the top part of the soil, in the very top soil. We look at that as an indicator of improved soil health. But I just want to make the point that, you know, it's really not just the top 6 inches here. Soils are physically complex throughout their entire profile and depth. So in the subsoil of the drummer on the right here, there's these beautiful prismatic structure that has an impact. Some of these macropores that roots can grow down, water is infiltrating. So soil structure, the way soil is aggregated, and its physical components, soil texture, are really important for the physical properties. And all of this means that soil is extremely physically complex. If we look at sand, silt, and clay particles, we can start exploring some of this complexity. So these are images of sand, silt, and clay particles under these two. The sand is actually under a light microscope. The clay is actually pictured here under a scanning electron microscope. So you would never be able to view clay particles like this, obviously with your naked eye, or even under a light microscope. You need to use a microscope that can have resolutions of around 1/1,000,000th of a meter. So this is 1 micrometer, is this bar here. So this clay particle is about 1/1,000,000th of a meter in diameter. And one thing that we see as we look really closely at these particles is that sand and silt sized particles tend to be kind of, you know, roundish, cube shaped, like you would imagine seeing beach sand with your naked eye, of course. Clay particles, on the other hand, are typically shaped like plates. They're thin and they kind of have this plate-like shape. This means that they have an incredible physical complexity that we don't really realize when we're just looking at clays as, say, a lumped mass, you know, in bulk. But when we break them down to their individual particles, we can start to understand some of this amazing physical complexity. And to illustrate that, I just want to give an example here. That physical complexity relates to the amount of surface area that's available in different soils. So if you can imagine, what I mean by surface area is if you could take every soil particle and peel away the surface, like if you had a sand particle, I have a teaspoon of coarse sand here. If I could take this sand particle and unroll it like a ball, if I pulled all the surface off of a ball and laid it out on the floor. So one way to visualize the sheer physical complexity of these soil particles is doing a thought experiment. So if I have a teaspoon of a really clayey, fine textured soil here, a teaspoon of a sandy soil, what would be the total amount of surface area if I laid all those surfaces of the particles out? Turns out that the clay has about 5,000 meters squared, and the coarse sand has only about 0.03 meters squared. So that coarse sand, if you could lay it all out on the floor, the surface area would be about the size of a front of a textbook, maybe an average textbook. The clay teaspoon, you've got surface area about on the order of a football field. And so we're talking about exponentially more physical surface in finer textured soils than sandy soils. That's one of the amazing physical complexities of soil, is that this is not a linear relationship. The finer the particles get, the more the surface area gets really, really, really quickly. And so the reason that is that every little particle in a fine textured soil has space around it. So I've got here in the middle, I've got a picture of an aggregate, a soil aggregate that's composed of some silt and clay sized particles, a couple coarse silt particles in here. And then I've got a sand grain at the same scale. And what you'll notice is that the spaces in this aggregate, these aggregates are approximately the same size. This aggregate's approximately the same size as this sand grain. But there's no spaces really in this sand grain. There's no pores. In this aggregate that's the same size, you can see around every single particle, there is some space. And so the pore space, the available pore space, and the surface area in a finer textured soil with all of these small particles is going to be exponentially more. And so this has implications for water retention, water storage, gas exchange, chemical processes, which I'll talk about in a second, which rely on soil surface area. So there's just this amazing physical complexity that we don't really appreciate when we just look at soils in bulk. I also want to make the point that the fabric and structure of soil, not only is it complex, but it affects all of these other things. As I said, water infiltration, gas exchange, plant root growth and development, and chemical processes. And that the fabric and structure of soil actually changes depending on where you are in a soil. This is just one example. This is a picture of a soil I took from Wahoo, Nebraska. And you can see that within this soil, here's kind of the topsoil here. This scales in centimeters, by the way. Sorry, it's not in inches. So this is probably, you know, the top 6 inches up here, so top foot. But there's actually some really different structural types throughout the soil. So there's kind of platy structure, which I've zoomed in over here near the top. There's some angular blocky structure, some structure that we would call prismatic. So you can imagine that plant roots, water, gas exchange, as they're encountering this complexity of soil structure, that's all changing the way that these things behave. And so really understanding and appreciating the complexity of soil physical arrangement is important. This is a really cool study where they did an X-ray CT scan using a medical device, X-ray CT scan of a cube of soil. And you can see, so they've been able to reconstruct in 3 dimensions this cube of soil. This is the solid space. These are all the soil particles, sand particles, silt, clay. And this is the pore space. And I think these new ways of visualizing soil are so important because they really show us how complex the empty, well, it's not empty, but the pore space in soil really is. It shows us how interconnected these pores are, how tortuous the routes that water would have to take, for example, to move down through the soil. These are not straight straws. There's a wide range of pore diameters that we can see in here, and they're of varying length, shape, and orientation. And so the full architecture of soil is really this combination of not only the sand, silt, and clay percent, which we're most familiar with, but the structure, the aggregation, the pore size, space, and complexity of the pore network. That's really the first physical manifestation of the magic of soil, is just how physically complex they are. The second piece of this is how chemically reactive soils are. So soils are not an inert material. A lot of times, particularly, you know, if you look at the historical development of the field of soil science, it really started back in the 1800s and early 1900s, kind of treating soil as an inert material. That's where a lot of the origins of soil science came from, until we finally started understanding just how chemically reactive soil is. So soil, you know, we talked about the physical surfaces. Those physical surfaces are basically a substrate for all of these amazing chemical and biochemical processes to occur. And when we zoom in on them, we really can begin to understand how amazing this substrate is. These mineral soil surfaces provide a substrate for all the processes, biochemical and chemical processes that occur in soils. And they basically are mineral particle surfaces that interface with other soil components. On the right here, I've got a scanning electron micrograph image from a researcher at the University of Bremen. And what it's showing here is there's actually soil particles covered up under these kind of goopy stuff you see here. That's actually probably organic matter, organic molecules coating the mineral surface of those soils. And then you can also see a lot of biological activity. There's bacterial cells, there's strands of fungal hyphae that these bacterial cells are growing on. So these mineral surfaces in soil are not just inert sitting there, they're actually interfacing with biological activities. They're interfacing with other soil components like organic matter, maybe iron oxides, and they're basically the seat of soil fertility and chemical processes, and they provide the space for all of these biological activities to occur. I also want to make the point that next generation bleeding control techniques rely on the surface reactivity of common soil minerals. So unfortunately, over the last 20 years, there have been major advances, fortunately or unfortunately, there have been major advances in military techniques for controlling bleeding. And some of those advances, the first generation actually used ground up kind of shellfish shells, basically, to kind of start the coagulation cascade and stop traumatic bleeding. We've now moved to a second generation where we actually basically have kaolinite impregnated gauzes. Kaolinite is one of the most common soil minerals worldwide. And basically in a sterile purified form, it's used now to activate the coagulation cascade in these second generation bleeding control products. And basically what happens is kaolinite is this super common soil mineral, and its surface carries a slight partial charge. And actually what happens is the kaolinite surface, because it has some bit of chemical reactivity, actually binds with human coagulation factor 12, which is actually the start of the coagulation cascade. This molecule that we're looking at is the start of how we actually form blood clots. And it leads to the cross-linked fibrin clot formation, which is what we see when we start forming blood clots and they start getting kind of hard and more resistant. And so kaolinite, this very common soil mineral, when it's impregnated in gauzes and put on a wound, actually starts triggering this human coagulation factor 12 and then begins this process of clot formation. So there's this amazing reactivity of these extremely common soil particles that we take for granted. And we're just learning some of the properties and uses of these. Really small soil, clay, and organic matter particles, which we call colloids. These are typically particles that are less than 2 microns, less than 2 millionths of a meter in diameter, are super important because they're mostly negatively charged, particularly in our part of the world. There are some parts of the world where they can be positively charged. In our part of the world here in the Midwestern United States, most of our mineral and organic matter particles, our small colloids, are negatively charged. And because they're negatively charged, they get surrounded. The soil water is not just pure water. It contains all sorts of ions and molecules. A lot of those positively charged ion and molecules are really important for plant nutrition. A lot of the major plant nutrients, the way that they get taken up in plants is as positively charged ions from the soil water. And so because our negatively charged soil colloids are sitting there as these chemically reactive surfaces, and we've got positively charged ions in the soil water that eventually will make their way into plants and be plant nutrients, those positively charged ions are stuck to, or adsorbed is one way we call it, just like Velcro. They get stuck plus to minus to our soil particles. And so what that means is that our soil particles are surrounded by these huge swarms or clouds of positively charged molecules and ions. And there's 100 to 1,000 times more ions that are absorbed to the solid phase of soil or stuck to the solid phase than there is out in the soil water. So what that means, if most plants get their nutrients from ions in the soil water, it means there's actually 1,000 times more of those ions stuck to the solid that the plants can't yet see. And so there's this huge chemical reactivity. And these ions are in equilibrium with the soil water. This is the process we call cation exchange. So there's this constant swapping of ions that are free to move in the soil water with ions that are stuck and Velcroed to the soil solids. And this is a process that's happening all the time, and we can never visualize it physically, but it's extremely important. It's probably one of the most important reactions that occurs in nature. One analogy to think about cation exchange that I really like is a beehive analogy. So you can think about the soil particles, the colloids, as like the honeycomb, the beehive surface. And basically the swarm of positively charged ions, most of them are plant nutrients, are stuck to that surface, but they're moving, right? They're not stuck and just stuck there permanently. They're actually like vibrating and moving. So if you think about a tiny clay particle in the soil, it's surrounded by this huge swarm of bees or ions that are constantly vibrating and moving around. The ions that are out in the soil water, our plant nutrients, are just a small fraction of that. And they're like the bees that would be out. I don't know much about bee biology. Others probably do on this call, but they're the ones out, whatever they're doing, foraging, bringing stuff back to the hive. That's only a small fraction. The bees that you see flying around are only a small fraction of the bees on the hive. I think this is a really great way to visualize the chemical reactivity of soils and cation exchange, the differences in cations in the soil water and on the soil solids. Okay, soils are also way more biologically active than we've appreciated. And we are just now, with new techniques in genomics and metagenomics, cracking open this black box of soil diversity, microbial diversity and activity in soils. And so, you know, we're entering this new phase. We have been entering this new phase. Our ability to look at the microbes in soil has changed dramatically. And we're appreciating things like, for example, this paper was looking at the global distribution of nitrogen cycling traits that are present in soils. And so you can see just this huge diversity of bacterial classes and species that actually have nitrogen cycling traits in them. The original way that we understood nitrogen cycling in soil was by taking organisms that could largely be grown on plates, agar plates in the lab, like potato dextrose agar or other types of media. But what is true, what we know now is that the microbes that live in the soil that can grow well in a lab on, say, a potato plate are only a fraction of the microbes that actually are out there. And that's because there's some microbes that maybe just don't like growing and they don't like the conditions in a lab. They're not going to grow on a potato dextrose agar plate, but they might be highly active in the soil. So cracking open this black box of microbial diversity in soil is really important. And we're on the verge of some really amazing new insights into the biological activity and functioning of soils. So the flow of energy and carbon into soil are linked. The energy that comes from our food, I ate my Wheaties. I actually love Wheaties. I don't say this as just a random term. I love Wheaties, and I actually ate Wheaties this morning. So I ate my Wheaties this morning. I'm getting energy from those Wheaties. The way that I'm getting energy is I'm consuming the Wheaties that have carbon in them. The carbon in those Wheaties came from plants, wheat, and those wheat plants, they actually brought that energy in from the sun through photosynthesis. So the energy that's driving my body from my Wheaties right now is actually solar energy. I mean, it's stored solar energy, but it came from the sun. The sun is the great nuclear reactor of our world. It's amazing. It's 93 million miles away, and you can stand out on a day, a hot July day, and feel like you're burning up because there's this nuclear reactor 93 million miles away that's literally flinging particles at us, and it's high enough energy that we can actually feel warm when we're sitting out in it. So all that energy is converted from its kind of particle energy, electromagnetic energy, into chemical energy by plants that are photosynthesizing. And that chemical energy is then stored in the plant tissues, which can become part of the soil organic matter. And so energy and carbon are the same thing going into a soil. They're linked. So when we talk about building carbon in soils, a lot of times in soil health, we're focused on, can we improve the amount of organic matter? Can we improve carbon? What we're really talking about is increasing energy in a soil. If you're increasing carbon, you're increasing the energy in a soil. And that's important because it's that energy that actually drives microbial life. So increasing organic matter and carbon is not just about some physical thing. It's actually about increasing the amount of stored chemical energy in a soil that is then available to drive all of the life, the diversity of biological activity that we see in soil. Plant rhizospheres, a rhizosphere is just the area around the plant root. Plant rhizospheres are really the hot spots of carbon and energy input into soils. These rhizospheres are where the action is happening. So if we look at, I'll show you an image in a second, but if we look at how microbes are distributed in soils, a lot of times microbes are clumped around plant roots, because that's where plant roots are kind of leaking out some of this carbon, some of this stored chemical energy. It's like going to the old country buffet, right? If you have a choice and you're hungry, you're not going to sit in the parking lot of the old country buffet. You're going to go into the old country buffet where all the food's available. It's the same thing with the rhizosphere when it comes to microbial activity. And there is so much intimate root soil contact that as these organic compounds are exuded by plant roots, there's microbes right there, right living on those physically complex, chemically reactive soil surfaces that are interacting with this food that's feeding this whole soil food web. We also know that because the flow of energy and carbon are linked, that microbial biomass is closely related to soil organic matter content. So again, as you increase soil organic matter or carbon, you're increasing the amount of energy in that soil, and that means that you're going to have more microbial biomass. So generally speaking, soils with more organic matter have more microbial biomass. And it's very simple. Again, it's like the old country buffet. The more food you have, the more people are going to be there eating. So it's basically that simple. Microbial biomass is usually, if you look kind of globally, it's maybe 1 to 12% of the total amount of soil organic matter. Good average of about 5%. So it's a pretty significant mass when we scale it up on a per acre basis. The microbial biomass in a soil could be, the weight of 2 cows, for example, might be in microbes per acre. The new ways that we have to visualize the way that microbes are distributed in soil really show us the diversity and heterogeneity in terms of where microbes are located. This fish staining fluorescent in situ hybridization. That's what FISH stands for. But really, it's a way to visualize where certain microbes are. And so this is in a soil aggregate, and it's basically lighting up where the microbes are. And you can see that the microbes are not homogeneously distributed throughout the soil. They're clumped, and they're probably clumped around sources of food or energy like soil organic matter. So the spatial distribution of microbes is not just even. Microbes are smart. They're going to grow where there's food. It's that simple. I also want to make the point, another application that I would be remiss not to mention when it comes to soil biology is that modern medical revolutions have been dependent on soil microbes. So this is just one example, but actinomycin was first isolated from soil bacteria in 1940. And it was the first discovered antibiotic that also has anti-cancer activity. It's a very common antibiotic, class of antibiotics, but actually most classes of antibiotics that we use came from soil microbes. In fact, actinomycin was isolated from suspensions of garden soil. So we are surrounded by this amazing diversity of microbial life, and really soils are the only the environment on Earth that is the most diverse when it comes to microbial diversity, because they are so complex. We don't have other environments that are as complex as soil, and so that explains the huge diversity of microbial life that we see. And these microbes produce a really stunning array of biologically active compounds that we're just beginning to understand. There was a study that was done in 2018 where they looked at New York urban park soils. Okay, so New York City, urban park soils in New York City. And you might think, well, those must be terrible soils, right? They're in the middle of this urban area. What could possibly be there? It turns out incredible diversity of microbes there. So it really doesn't matter whether you're in an urban area or a rural area. There's this huge diversity of microbes in soils, and they found that not only that, there were classes of molecules that look like some of our antibiotics that were all over the place in these New York City urban park soils that we have yet to understand and discover. So all of these microbes that are living in soils are just going about their living, doing their thing, but there's a huge range of compounds that they're producing, and we are just cracking the surface of what those compounds are. This microbial activity really powers the flow of energy going up the soil food web. So microbes are constantly working. They're the workhorses of decomposition in soil. And this is a potato field, a picture that I took in central Wisconsin on a June day. But basically, if you could imagine a July day on a per acre basis, the microbes in a soil are decomposing organic matter and putting out about as much heat as kind of a small outboard motor. So there's a lot of activity that's happening that we just cannot see, but it's part of the energy and gas exchange that occurs in soil. And all of that is what powers the soil food web. Soils are literally the factory of life. And the soil food web, not just the microbes, but as we start going up the food web to things like nematodes, arthropods, microarthropods, earthworms, and then we get into larger things that start linking to the terrestrial food chain, like ground-dwelling mammals, for example, that birds might be dependent on, et cetera, et cetera. So the soil food web is really the foundation of the terrestrial food web. The soil food web provides this basis to transform the solar energy from the sun into stored chemical energy that really powers our world. So soils are more physically complex, chemically reactive, biologically active, and diverse. I already talked a little bit about soil diversity. One of the things that sticks out to me when I think about soil diversity is soil color. You can see this wide range of soil colors here in the selection of soils that I have from around the world. But soil color is a really critical soil property, and it gives us some unique clues to how soils formed. There's basically three major coloring agents in soils. There's the soil minerals themselves, which for the most part tend to be gray or white. There's iron oxides. Iron oxides are just rust. So there's a lot of iron in soil, and just like metal rusts when it's sitting out, that iron rusts and turns into these iron oxide compounds, which coat soil mineral particles. And so soil mineral particles are really coated by these iron oxides and by organic matter. And organic matter, of course, looks dark in color when it's well decomposed. Part of the reason that organic matter looks dark when it's well decomposed is because, it didn't start that way. It started looking like a plant tissue, like green or light brown, whatever color might be dried or living plant tissue. But you throw it all into the soil, and as those molecules decompose, they become less ordered. And when they become less ordered, they absorb light. They absorb more wavelengths of light. And the more wavelengths of light a substance absorbs, the more it looks dark to our eye, because there's fewer wavelengths being reflected to give it color. So soil organic matter is dark because it becomes well decomposed by microbes in the soil. And organic matter and iron oxides are basically painting the surface of soil mineral grains. So underlying the color that we see in most soils is actually just these maybe clear gray or white colors of the mineral grains themselves, but they're painted by these molecules of iron oxide and organic matter that give them earth tones or darker colors. Here's just a cool thing I did in the lab. So I did this for my basic soils class. I just picked up some topsoil from our campus fields behind our buildings. And so this is just from the St. Paul, our experiment station. You see here's an aggregate. We broke the aggregates down in the lab into their components, and we extracted the organic matter and the iron oxides from a little bit of this soil, not all of this, but a little bit of it. And you can see that the sand, silt, and clay particles over here basically look gray. That's the color of the mineral grains themselves. What's imparting this color that we see to our eye is actually the paints on those mineral grains, which are the iron oxides and the organic matter. In this case, organic matter is dominating the color that you see in this topsoil here. So the diversity of soil, the color that we see, is actually an indication of some of the properties of that soil. And topsoil colors really vary across the United States. This is a great map that was put out by USDA NRCS a while ago that shows the variability in topsoil colors across the US. One thing that really sticks out to me, I talk about to this a lot with my class, is just how in the north central US, we're used to seeing these dark colored, our prairie soils, for example, our dark colored prairie soils. You have a lot of those in Illinois. These soils are really unique because they are so fertile. They have a lot of organic matter. If you go to other parts of the country, you really don't see that as much. So we get used to these colors of topsoil that we see in our part of the world, and just recognizing how unique those are, I think is really important to connecting with and understanding our soil resource. If you look at subsoil colors, we see even more. So, a lot of the southeastern US, the unglaciated portion of the southeastern US, the soils are older, they're more highly weathered, and we get more accumulation of iron oxides in those soils. So they look more red or yellow or orange. A lot of our soils in the north central US and Illinois tend to have our yellow or grayish colored subsoil. That's because they're actually a bit more, they're a bit more poorly drained than some of the soils in other parts of the country. And that drainage is actually obviously a challenge sometimes for management. Sometimes obviously we drain our soils to get rid of the excess water, but not only that, it's also important because that sub-irrigation is part of what makes our soils so fertile. Water doesn't just run very easily through our soils. And so really important to place in context the soils that we're managing. Even if all the soils in your neighborhood look the same, recognize that these are globally unique soils that deserve their own thought and management. And every soil has been uniquely shaped by a set of dynamic environmental factors. So I mentioned a couple things about why the soils in the north central US are different from soils in the southeast, for example. Part of that has to do with the time that they've been developing, the organisms that they're growing on, our climate, et cetera. But every soil in the world is a unique entity. Just like every person is different and unique, every soil is different and unique. And when you meet your soil, greet it as a unique entity as it is, and it's going to be changing throughout whatever property you manage. You're going to have a whole host of unique soil entities on that property, and they all deserve our own unique perspectives and introduction. So I want to wrap up with this thought. Soils are more physically complex, chemically reactive, biologically active, and diverse than we can imagine, and our management of soil impacts human and environmental health. So now that we've talked about some of those first basics, I just want to touch on how management can dramatically impact the properties of soil. So this is a side-by-side we did. This was in Granite Falls, Minnesota, which is west central Minnesota, on an operational farm. The soil on the left, these are topsoils, had been in prairie grass for about 12 years. And you can see that this prairie grass has contributed a lot of root structure, which has formed this kind of granular aggregation in this topsoil. This same soil on the right was annually tilled, and it's got kind of this subangular blocky or even massive structure to it. So imagine water falling on these soils and the difference in infiltration, water infiltration, gas exchange, plant root growth. Plant roots are going to have a harder time growing through these soils. So part of our management of soils has to think about how we're impacting soil structure, because soil structure is so important for these other things. If we go back to our new ways of visualizing soil, this is the same 2014 study I showed an image from before, where they did an X-ray CT scan of some blocks of soil. This is an example of an uncompacted soil, the solids and the pore space. This is what I showed you before. Here's an example of a compacted soil. This is one way to visualize. First of all, the solid component is much more mashed together. And what it means is that the pore space is much less connected. You can see there are pores, but they're not very connected. They're kind of isolated, they're smaller. And so this would lead to decreased porosity and decreased water infiltration. So soil structure and the architecture of soil can be dramatically affected by management, and that can have real world impacts for things like plant growth and soil health. Soil erosion and loss is occurring at unsustainable rates around the world. It doesn't matter where you go, we can find examples of unsustainable soil loss. I show these side-by-side examples of just two pictures that I took. One in Minnesota, here's a gully forming in this beautiful prairie soil in west central Minnesota. And then on the right is a soil that is shallow to bedrock in Tanzania. I took this picture. The soil's actually been eroded in some cases right down to the bedrock, and people are still trying to plant in there. So soil conservation is a challenge for all people in all generations. And we have a unique opportunity in the US Midwest to conserve soil on really highly valuable agricultural lands. This is a study I did with one of my colleagues about 4 years ago, and we took the soil maps that were available for the conterminous US and pulled out all the soils that had been mapped as eroded soils. And you can see that, you know, Minnesota, Iowa, Wisconsin, Illinois, northern Missouri, there's some anomalous things here because these were mapped by counties. So you see some random patches. But in the big picture, it shows that we have this huge opportunity to improve our eroded soils in the US Midwest and also conserve the soils that we do have. And we want to avoid things like gully formation that happened in the 20s and 30s in the driftless area in Wisconsin, or in the Piedmont of North Carolina, Georgia, et cetera, where a lot of those soils were gullied and eroded in the 1800s, actually. And so the red and green here, the green is actually showing agricultural lands that are no longer cultivated, but they were eroded by agricultural activity. And you can see that a lot of the southeastern US, those soils were highly eroded in the 1800s, and they're abandoned now. A lot of them are just, there's forests on these soils now. The driftless area is similar. There's a lot of soils, there's a lot of landscapes in the driftless area that used to be cultivated in the early 1900s that are no longer cultivated. And so the challenge is, how do we avoid this story from repeating itself on the lands that we manage today? And so a lot of that has to do with soil health and soil conservation. So I'd like to just end with this thought. And it's a quote from Charles Kellogg that I really like. All life depends on the soil. There can be no life without soil and no soil without life. They have evolved together. Bringing that ethic into our concepts of soil management and soil health, I hope, will help us all better treat our soils as unique entities, tailor our management to specific soils that occur in the lands that we manage, and overall improve human and environmental health. So I will end there, and I believe we have a bit of time for questions if there is time.
We do indeed have some time for questions, and we have a couple of questions. Those of you who have not put them in the chat box yet, go ahead and put those in. I'll see them and we'll get them asked. There are a couple quick questions relating to your discussion early on, Nick, of the connection between human health and soils. This person writes that I've read reports that many food crops have sometimes about 40% less of certain nutrients than in the 40s or maybe in the 70s, like calcium and vitamin C. Can you talk about that first and whether that's actually true from your research, if you've got, or something you looked at? And does soil degradation or focusing on NPK fertilization contribute to this, and how might we increase the nutrition?
Wow, good question. So I am a researcher, so I'm going to be careful to stay in my lane of research.
Okay.
But I do have colleagues that I've interacted with, and I might be able to share some of the things that they've told me from their research that might apply here. So what I understand from a couple of my colleagues in our horticulture department is that it is true that basically, and it makes sense, the nutrient content of a lot of our, especially fresh vegetables, for example, our fresh produce, decreases over time past harvest, right? So the nutrient content, whatever those nutrients are, vitamins, whatever they are, some of them are going to start degrading post-harvest once that plant is harvested. And so if you think about our food system, we do certainly live at a time where we're eating more things that have been, the time since harvest has increased because we have more cold storage, we have new ways of transporting things. And so we have this incredible diversity of things that we can buy at the supermarket. But the time since harvest in terms of when we're consuming them is probably more than it would have been in the 1940s, 1930s, where there wasn't as much cold storage. You were eating more things that were probably grown in more regionally than nationally or internationally. So I don't want to step outside of my bounds and say I know a lot about this from directly my research, but I would say that I think there's a theme here that's probably true, which is that we're eating food after it's been harvested for a longer period of time, and that may relate to decreases in nutrient content. And that's just the reality of how we distribute food. And the second part of the question was?
Let's see. So, and does changing fertilization work to improve nutrition?
Oh, human nutrition.
Yes.
Okay. That's a tricky one. I don't want to stray too far outside of my lane, but what I will say is that we know that inputs of nutrients we're understanding more and more about how inputs of nutrients affect biological activity and diversity in soil. So I think we're probably going to begin to understand that a bit more. My sense is there's probably not a direct link between adding NPK to a soil and the nutrients that we're consuming, except for maybe protein content. There could be some more direct links there. There may also be some indirect links through soil biology that we're only beginning to understand. So I think I would say the science is out on that.
We're running short on time, so quick answers. Are there properties of different crops, whether they're commodity or cover, that are beneficial to the development of soil structure?
Yeah, so probably just briefly, if we think about the properties of crops, and I'm not an agronomist, so I'll leave that to the cropping systems folks, which ones in particular. But I would say, if you think about it, what is an ideal crop for soil structure? Well, you want something to be deep rooted. You want it to have a fibrous root system. So the more fine roots that you have, the more carbon organic matter is going to be input into the soil, and the better the aggregation is going to be. So deep roots, fine rooting system, those are two major ones. And there's also some crops that are more or less leaky in terms of how much carbon and organic matter they turn over, and that would be another piece of that. So I think that there are general strategies of plant growth that would contribute to beneficial soil structure, yes.
Nick, thank you so much for being with us today. And actually, soils are pretty darn magical.
Thank you.
I really appreciate you taking the time with us, and what a stunning presentation. I appreciate that too. So thank you so much, and hope the weather there in Minnesota is good. I really appreciate you being here.
Thanks, Todd. Honored to be here. Appreciate it.
Let's move on now. That, of course, was Nick Jelinski. He is from the University of Wisconsin-Madison. He did get a PhD from the University of Minnesota. And he got his, he got his BS and his MS from the Universities of Wisconsin and Madison, and he is at the University of Minnesota. Now let's move to Illinois, where Stacy Zuber is a soil health specialist at NRCS. After growing up on a farm in southern Illinois, she received her doctorate in crop sciences from the University of Illinois, and then worked for several years in Indiana and Missouri, conducting on-farm soil health research. Thank you so much for being here, Stacy. And I'll make note that if folks have questions for Stacy, they can put them in the chat box, but there'll be two presentations before we get to those. So good morning to you, Stacy. Thanks for being here.
Good morning. Thank you for that introduction. I am happy to be here with all of you to be able to talk a little bit about soil health, soils in Illinois. So actually, this is the perfect timing to come in after Dr. Jelinski's presentation to kind of put a little bit of context to a lot of the information he shared and kind of put that into context with what we have here in Illinois. So I'm going to share this with you if I can. So I am the soil health specialist with the NRCS here in Illinois. This is a fairly new position here in Illinois, and the soil health specialist positions have been established in a couple other states around us for a number of years, but this is new for Illinois, and this is kind of part of a push to have a greater investment, more significant investment in soil health, more of a priority in soil health. That's kind of started at the national level that we're also trying to bring here in Illinois as we're developing more of a strategic plan to increase engagement with soil health, to increase outreach and discussion about the importance of soil health across the state. So as part of that, I wanted to talk today a little bit about the soils of Illinois and how the differences of those soils can impact the soil health and how we talk about soil health across the state. So, on the screen here, I'm just showing, maybe you've seen this poster before. This is a Soils of Illinois poster showing some of the different soil series that we have around the state. And, we have significant differences in the soils. Dr. Jelinski talked about some of those dark soils, and that's what we have across central and northern Illinois in our drummer soil, the Illinois state soil. That's one of our mollisols, our prairie soils that we have. We have Ipava, which is over in the western side of the state. That's one of the even deeper, have a deeper topsoil there. And Catlin, those are some of our, just examples of some of the soil series that we have that are these black soils, the very dark topsoils, our mollisols, and those are forming, in that prairie vegetation for over, hundreds and hundreds and hundreds of years, that those prairies vegetation has accumulated and developed that very dark organic matter on the topsoil. And as Dr. Jelinski mentioned as well, a lot of these soils are poorly drained, and that's contributing to the accumulation of that organic matter over time. So as we have poorly drained soils, we have, they sit with water, they have standing water on them for a long period of time. And that saturation of those soils is creating anaerobic conditions. We don't have oxygen available to the microbes, and many of those microbes that are responsible for the decomposition, for the mineralization of that organic matter, breaking it down, are aerobic. They require oxygen to do their job. So, we kind of have to contribute, or, give props to those microbes and that poorly drained conditions that they had the mineralization, the decomposition of that organic matter was slowed. So as residues from the prairie, from the grasses accumulated over time, they weren't breaking down nearly as quickly as they were accumulating. And that led to that, big buildup of organic matter in our soils, that very thick topsoil across, much of the state, the central Illinois area, the northern Illinois area, with these very dark topsoils with high organic matter. But now, since many of those soils have been drained so that we can farm them, so that we can, grow crops, and then we needed to drain them in order to use those fields. But because of that, both the, disturbance of the soil by plowing those fields, by tilling those fields, as well as the drainage that we've, had to put in place to be able to use those soils, both of those have contributed to the loss of organic matter in those. Sometimes you hear the fact that as soon as many of these fields were put into agricultural production, we lost 50% of the organic matter. And that's probably true, maybe more on some of these soils. And even with that loss, we still have very high organic matter across many of them. But we need to be realistic that, as a person who's passionate about soil health, I would love to be able to improve the soil organic matter on all of these soils back to where it was. But we need to be realistic that if we're going to keep those soils in production, we're never going to be able to get them back to their original levels on those, because we have already changed the drainage. And that was such an important part of the accumulation of organic matter on those. But we still have those high organic matter soils across that part of the state. But then if we look at the southern Illinois and somewhat in the parts of the western Illinois area, we have, alpha soils. Those are our forest soils, our timber soils. There's much less accumulation of organic matter on those soils. And a lot of them in southern Illinois also, they were glaciated much earlier. So they're older soils, they're more weathered in the southern part of the state than we have in the northern part, where that was glaciated much later. So we have that difference in the organic matter. And then also in southern Illinois, on those older soils, we also have clay pan across much of the state, which can cause, restrictions of root growth and can cause restrictions for the water infiltration into all the way throughout the soil profile. So, we have to take those differences in the soils into consideration when we start talking about soil health. So, when we're talking about the soil health, we're focused on, the main definition of soil health is the continued capacity of a soil to function as a vitally living ecosystem. And the main thing I want to focus on in that definition is function. So these soils, we're focusing on how the processes are happening, how the cycling of nutrients are happening, where the soil structure is being formed, or water infiltrates. We're focusing on a lot of those different processes that are happening in the soil. And so when we're looking at soil health, we want to see how those processes can be improved. And regardless of whether you're starting out on a high organic matter soil in central Illinois and northern Illinois on those mollisols, or you're on an alpha soil in southern Illinois, you can see and will see improvements in those processes, in those functions, regardless of where you're starting. You can see those improvements if you're adopting soil health practices, but we need to kind of think about them a little different. We need to focus on different indicators in particular. So for instance, a lot of the times that soil organic matter, we use that, and a lot of the times in many of the discussions when we talk about carbon markers and we talk about soil health, we focus on soil organic matter as the be all and end all of soil health. And there's a good reason why. It's very closely related to the soil functions, all of the different soil functions, all of the processes throughout the soil. You know, it's a food source for microbes. It's related to that soil aggregation. It helps with water infiltration. It's related to all of these processes. But if we're focused entirely on that, it can be, you know, a little bit problematic to focus entirely on that when you're looking at soils like we have in Central Illinois and Northern Illinois that already have high levels of that organic matter. Because when you're starting out at high levels, it makes it very difficult to accumulate more. Even if you make all of the soil health management practice changes, and now you're doing cover crops and you're doing no-till and maybe you're grazing livestock, you're doing all of the things that are suggested, it's still going to take time for that organic matter to change. And a lot of that comes back to that drainage topic. You know, if we're draining your field so you can still, you know, grow crops on it, you're never going to be, there is a limit to how much more organic matter you're able to accumulate on those soils. You're already fairly high. It's going to be accumulating in slow increments. However, we can still see big changes and big improvements in other processes within that soil. We can see improvements in the soil structure and the aggregation and how those particles are being held together. We can see improvements in the water infiltration. We can see more diversity in the microbial community. If you're adding diversity into your crop rotation or your cover crops, we can see more diversity in the microbial community, which can lead to, you know, different cycling of nutrients happening. We can see disease suppression as another benefit potentially from a more diverse microbial community. So it's really important, and I think that's the main takeaway I want to give you today from this, is that regardless of where you are in the state, if you can adopt these soil health management practices, you can make changes, and that can improve the soil processes in your soil, the functioning of that soil. But you don't need to focus entirely on the organic matter. In Southern Illinois, just looking at organic matter, the changes in that can be a very good signal that the other processes are improving as well, because you're starting out at a fairly low level. But if you're already starting at a high level, it's only going to be confusing to look at that organic matter, because you're going to see fairly small changes, but the rest of your processes and functions within that soil, the soil health, can really improve even without changes in that organic matter level. So I just wanted to share that with you today. And if you are interested in more information about the soil health and soil health management practices, I highly recommend, you know, giving a call to your local field offices, talk to them about how you can make these changes and adopt some of these practices to improve your soil health. So
Thank you,
thank
Stacy.
you for your time.
I appreciate it. If you've got questions, of course, for Stacy, you can write those in the chat box and we'll get to them as soon as we can, but not until after we've heard from Joe Rothermel, who is a farmer from Broadlands, not too far away here, with background in aviation and engineering. And I have had a sneak look at some of his PowerPoints, and that engineering background clearly shows he has been an active member of the Champaign County Soil and Water Conservation District for about 18 years. Joe, thank you for being here. And we do appreciate you taking your time on this Wednesday to help us learn a bit more about what you've been doing on the farm there.
All right. Thanks, Todd, for the introduction. And thanks for everybody who's joined in on the webinar today. Also want to thank the seminar planning folks for letting me present today. And I've been asked to talk about my farm operation and how I got to where I am, and a little bit about the STAR program and my involvement in that. So I'm going to back up one here. There we go. So you can see from the first slide here, my farm is in the Broadlands area, which is southern Champaign County, mostly drummer Flanagan soils. I also chair the Soil and Water District here in Champaign County. Yeah, I've been in the STAR program since it started. I don't have a 20 sign yet, but that's because I filled out the forms, which, by the way, if you're in the STAR program, are due February 1st. So And last but not least, these are my kids, both FFA and Ag students at Heritage High School. Just a little to let you know kind of who I am and where I come from. Before farming, I worked at Douglas Aircraft out in Long Beach, California. This is back in the 80s. On the left is an MD-80 on the ramp that's not done. And on the right, we're working as inside an MD-80 fuselage. And so I show you this and tell you this to let you know I really have no formal ag education or training. This is what I went to school for. Okay, then in the early 90s, moved back to the farm. My dad retired from farming. And the first thing I did was to build this 20-inch row planter. Thank you. My dad at that time was planting corn in 36-inch rows, and I saw that and I said, well, we're not going to do this. It's like a waste of space. And so we did this for several years. And then I learned there's a lot more to growing crops than row width, although I liked growing corn in 20-inch rows. I think it's a great way to grow corn. At that point, I decided to focus not on row width, but on no-till practices. And so it took me a while to figure out how to no-till corn. And what really helped was adding these attachments that you see in the upper left-hand corner. And so this is kind of an outdated equipment, but the concept is still the same. So in front, you can see that's a floating row cleaner. I think it's a Terratine. And there's a single disc opener for applying nitrogen. And then there's a seed firmer on there, and we use that not only to firm the seed, but to apply starter fertilizer. And then it ends up with spike closing wheels and a drag chain to level off the furrow. So, and then you can see in the bottom picture that there's tanks for the starter, and at that time it was 28%. So this setup worked pretty well. We grew some pretty good corn with this old John Deere 7000 planter. And at that time I was also no-tilling beans with a John Deere 750 drill, which is pretty much a no-brainer. At this time, I really had no roadmap to guide my operation, and I was just kind of trying to figure out what to do. So sometime later, I started experimenting with strip till. There we go. See the picture on the left there. And I started attending the National No-Till Conference, where I heard a presentation by Dr. Joel Gruber on cover crops. That was around 2010. And that was my inspiration for growing cover crops. So at this point, I decided that if I'm going to grow cover crops and strip till, why not do them at the same time to save a pass? So I put together this front mount drill, which I designed to plant annual ryegrass. And then on the back, I'm pulling the strip till bar, and then behind that is a tank for liquid fertilizer next to the corn crop. And this worked pretty well, except the guidance system didn't really like the thing on the front, and I had to learn how to steer that. And it looked like this, which I thought that was pretty cool. We've got annual ryegrass growing between the rows, and then we got a nice berm here to plant into. The only problem with this is if you have any slope at all, it's going to become a gully where that berm is. So revision A, I added that little red Gandy air seeder to the strip till bar so I could plant a cover crop on the berm, and it just blows the seed out right in front of those berm builders, kind of mixes it in. And so that let me plant radish or rape on those 30-inch rows and keep the berm covered. And it looked like this. On the left there, I think that's actually rape growing. I had a plot there that year. And in between is the annual ryegrass that's planted by the front mount drill. And then on the right, you can see what it looks like in the spring right before planting, where that radish was growing. That's a really nice seed bed. It's warm and it's mellow and it's soft. And so at that point, I began to look at what was happening to the soil. You know, other people had been doing this, and so I started taking soil tests in that berm where those cover crops were growing to see what was happening. And excuse me, what I found out was that the rape increased potassium about 32% and sulfur about the same amount. The radish, a little bit less potassium, and sulfur about 27%. And so there was some benefit to planting those cover crops there, not to mention there's also cover crops growing in between the rows there. So there's some other biomass laying on the ground there. Okay, then I decided if I'm planting a tillage radish, I really need to be pulling a strip till bar. So I switched things around and put the drill on the back. Same concept, just in a no-till situation. What I call revision B. And then revision C, I built this air cart to increase seed holding capacity. I just built the cart, that white box, that's a Salford Valmar unit. And so I got the strip till bar back out and made a second floor behind that. And then finally, I made it so I could pull it behind this drill again. And this is what I used this fall for planting cover crops in both soybean stubble and corn stalks. And it works pretty well. All right, this is what it looks like. This was planted with a strip till bar. That's barley. I like to plant barley before corn instead of cereal rye because it's not as aggressive. Has a little bit less biomass, but it still overwinters. So you can see that was planted between the corn rows, and then on the corn row was radish, and it's decayed and gone. And so I just have a nice black strip there to plant into. Okay, this is my current planter setup. It has tanks for applying starter and 32%. The only thing different is it has spiked closing wheels and drag chains on it to turn on in that picture. Okay, just a few details on planter fertilizer for corn. I apply 5 gallons of 3-18-18 and zinc in the furrow, and that comes out via the seed firmer. This year I switched to 9-24-3. And then I apply 12 gallons of 29-004 and sometimes 10 to 12 gallons of 10-34-0 in a 3x3x2 placement. And that's done using this opener system you see there in the picture. And what I did there was I modified that John Deere single disc opener and I added another blade, and so I can place in on 3 inches from the row. And so this picture here was taken during a replant this last spring. So you can see it straddling that little sick-looking corn plant. And so what you see here is the complete fertilizer program I use for corn. I don't use a lot of dry fertilizer anymore. And, so I do this for a couple of reasons. One is so the fertility is placed close to the plant roots, and also so it's under the soil surface, so it's less prone to loss. All right, the other reason is because no-till corn needs early in. And you can see from this picture what happens if you don't put a lot of in on early. On the right this is my field. There's no in on there other than what's in the starter. Otherwise it probably look even worse. And on the left, there's probably 60 pounds of in that I applied with the planter. And so it's not that I didn't put any on, it's just that I ran out right here. And of course, it's right by the road where everybody can see it. So you can see in the background there, the four-wheeler. I'm trying to fix it with drop hoses, but if you're switching from conventional to no-till corn, you really should consider putting some nitrogen on early to replace that flush of nutrients that the field cultivator pass used to supply. And so this is also about the time the corn plant's setting the ear, about V4, V5. So like the agronomists say, we don't want our corn crop to ever have a bad day, and this corn would have several bad days if there's no N on early in a no-till situation. Okay, my current setup is, and don't use a lot of fertilizer for beans, partly because I'm trying to rely on the cover crop to supply some nutrients. I've done several biomass analyses on the cover crop biomass, and this is what you see up there on the screen is a typical result I get from a cover crop that looks like what you see here in the picture. This is cereal rye, and this particular one yielded about 3,000 pounds of biomass, and in that was about 86 pounds of N, 22 pounds of phosphorus, and 107 pounds of potassium. So I don't apply potash anymore in the form of 0060. About the only source I use for that is what's in the starter fertilizer. Okay, a couple of things I like about the drill. I like the narrow rows for weed suppression, and yields seem to be okay. You can see the numbers there on the screen. I did a yield check where I went out and planted alternating strips of beans with my no-till drill, and then my planter, which was in 30-inch rows, and the no-till drilled beans came out pretty good. And I'm not exactly sure what happened there. I assume the capacity of the narrow row beans to intercept sunlight kind of offset the really lousy seed placement that the drill offers. So I do plant a lot of early beans to allow me to plant cover crops earlier, and there may be some compromise between the bean yield and the planting date on the cover crop with these early beans, but this is a typical yield I get from planting a 2.5 bean in a no-till situation. But you have to consider that just using no-till saves probably $30, $35 an acre not doing the fall tillage. So that's worth 2 or 3 bushel an acre. Used to be 3, now it's 2. This market prices are good. I'm going to back up one thing I forgot to mention. What's in my shop right now, I'm building this roller crimp on it's not near done. You can see there I don't have the slats welded on the cylinder. That's the plan for this year. I want to try and roll and crimp after the drill goes through, not to necessarily kill the cover crop, but to just get it down in a mat. Okay, in the meantime, I decided to bring wheat back into the rotation. If you really want to grow a big cover crop, plant wheat. You can see here on the left is a split application of nitrogen on my wheat. And then on the right, that's the cover crop that I planted after the wheat came up. That's an 8-way mix, and has pearl millet in it, which dominated that year because it was kind of dry. So I kind of like wheat. Wheat prices are pretty good, and if you combine them with double crop bean prices, I think it's not too bad. Okay, this last wheat crop, I crossed some red clover into the wheat in February, and this turned out a lot better than I thought it would. 6 to 8 pounds there of red clover, just splintered on with the 4-wheeler. And I've got this massive red clover crop growing. All right, future plans. want to experiment more with interseeding. This is the drill that I originally had on the front of the tractor before I modified it to pull the air cart. It works real well for interseeding. Interseeding is a whole nother subject and requires a lot of thought and planning. Something I want to practice with. But this summer, I want to plant my double crop beans in 30-inch rows, and then go back in late July with this and plant cover crops in between the bean rows, just like this here, and see how that turns out. And I have to figure out how to cut the beans without running all the cover crop into the combine. All right, so that's kind of a little picture of my journey, and so people ask me, you know, why do I plant cover crops? Why do I do all this stuff? Because it's a lot of work, and it requires a different train of thought. There are basically three reasons for me. Number one, increase the capacity of the soil to function indefinitely. That's kind of my definition. Or in other words, improve soil health. And I think I'm making progress because we have dug several soil pits in some of these fields and compared them to soil pits in an adjacent field that was under conventional farm management. And so these pits are just like 50 feet away from each other, but the same soil type. So what we see is better soil structure and aggregation, greater capacity to infiltrate water, and more indicators of biological activity like earthworms mainly, but there's other bugs out there. And organic matter, I don't know about the other fields, but it's gone up about 0.7 of 1 point since I've started this. Okay, second reason, to prevent nutrient loss that results from events like this. This is a field I happen to be driving by. This is in Champaign County. It's probably not HEL. And so you can see there's tons of topsoil relocated on that. And so the result is, I suspect, a lot of loss of nutrients, lower productivity for the farmer, and increased nutrient load in our waters. So I'm sure these farmers had no idea this was going to happen. And this is the last thing they would want to happen, but it's just kind of a gamble nowadays. I just recently read an article that said data from NOAA showed that since 1981, daily rainfall events exceeding 2 inches have tripled in the Corn Belt area. So this can happen. Okay, same field, 7 days later, it blew. More topsoil loss due to wind this time. And this was bean stubble that had fall tillage on it. So soil erosion is one of those things that just won't seem to go away. In my area, there seems to be more and more fall tillage done on bean stubble. Okay, third reason, to meet consumer demand. The consumer wants sustainability in farming, and as a result, many supply chain firms are developing sustainability plans and are asking farmers to adopt sustainable farming practices. Okay, so now after all that information that I sought out and all the learning I had to do so I could farm this way, it became clear to me that we need a plan to help farmers adopt conservation practices. So through the Champaign County Soil and Water District Stewardship Committee, the STAR initiative was started in 2017. So the idea was to provide a way to guide and recognize farmers who want to adopt conservation practices. So for those who aren't familiar with the STAR program, this is simply a form, 2 pages. It's a checkoff list of practices that you use on one specific field. You know, it takes about 4 minutes to fill out, and it's free. And so the practices used for a field are given points established by our science committee. And then those points are primarily based on concerns for nutrient and sediment losses, but they also contribute to improving soil health. Those points are then converted to a star rating of 1 to 5, based on, again, the science committee. The STAR program uses U of I fertilizer recommendations, including amounts and application methods, based on the agronomy handbook. Ultimately, STAR is intended to provide a roadmap of how to improve the use of conservation practices. And another thing I like about STAR, it allows us to recognize farmers for their accomplishments. And the most common way is by this field sign you see here on the left. And anybody who's in the STAR program can get one of those if they like. But also, companies like Kellogg have been helping promote STAR. And so the STAR Farmer of the Year for 2019 was Tom Byers of Marion County. So he got his picture on a cereal box, kind of like Wheaties. Also, supply chains like ADM are encouraging farmers to use sustainable practices. And so ADM is using the STAR program, and they're helping some soil and water districts promote it. Just to give you an idea of where STAR is being used, it's now licensed in 71 counties in Illinois and Indiana. The State Conservation Associations in Missouri, Iowa, and just Colorado this Monday signed MOUs to begin to use STAR in those states. STAR is continuing to grow. All right, and if you're interested in getting into the STAR program, the best thing to do is go to the website, starfreetool.com. There's 3 different ways you could submit the field information. And so for this year, the field forms, which I showed earlier, are due by February 1st. So something to keep in mind. And another little side note, for those who are already in it, if you have fields in Kankakee, Piatt, or Champaign County, you're entered into a raffle to win a prize. In addition, for those of you who represent a soil and water conservation district that's already licensed, your office can win a gift basket for having the largest number of fields submitted. And I've seen what's in the gift basket, and it's pretty nice. So, then I'd like to end with thanking a few people that have helped me along the way. Joe Gruber for the inspiration. That was from his talk at one of the no-till conferences. If you're going to go down this road of regenerative ag or soil health, you really need some motivation or some inspiration, because it's a long-term process and you might not see a lot of changes up front. So you need something to motivate you. I want to thank Barry Fisher for the teaching. When I said we dug soil pits and compared them to conventional fields, he was the one in the soil pit. And he came out several times with NRCS folks for teaching them soil health. And so I got to be a part of that. So I'm very thankful for that. And also Terry Taylor, former Southern Illinois down in Wayne County. He was the guy I called when I had a question. Terry's been doing this for a long time. He was doing cover crop for pool. And so everybody should really have a mentor if you're just beginning with this. So this is probably one of the most important slides, because these things are really important if you want to go down this path. So that's the end of my presentation. Thanks everybody for listening.
Hey, Joe, thank you. What an interesting presentation. I have, there are a couple of questions, I think, for you. What has been the toughest part for you in the transition from one field cropping system over the years to the other? So And you didn't talk about conventional field crops to begin with. And I don't know whether you were actually ever in conventional tillage or not.
No, I was not. No, I started out in a no-till situation. So I didn't really have to overcome that hurdle of learning or getting away from conventional tillage.
And over the years transitioning from one engineering feat, I suppose, because it appears you have built most, if not all, or adapted much of the equipment. Which was the toughest to think about and develop?
Well, the toughest thing was to figure out how to plant the cover crops at the same time we're running the strip till bar. And so that was the hardest thing. But I enjoy that. It really wasn't much of an issue because I just enjoy that type of work. But the hardest thing for me is the nutrient management part of this, because we know cover crops recycle and supply nutrients, but still, I don't think it's really known how far we can go with that. I think we need to do more research in that area, because we don't want to short the crop of nutrients. So sometimes I felt like I'm walking the line between conventional and biological farming, because we still use soil tests and rely on those, but I don't think those standard soil tests really reflect what could be going on in the soil biologically.
How do you think you compare economically to the peers in the neighborhood?
Well, according to my PCM data, which I didn't talk at all about PCM, but that's another good program. It looks pretty good economically. And part of that is simply because of the reduction in tillage. But we've also reduced fertilizer inputs some. But like I said, that is really the challenging part.
PCM, by the way, you can find more, including the star links at precisionconservation.org. And Gary Schnitke is involved in the economics behind that one and gathering up that information, along with the Illinois Corn Growers Association and most recently the Illinois Soybean Association. We do have another question about the implements. As I asked early on, you built most of them yourself. Somebody wants to know about the interseeder. Do you think there are things that you can purchase out there that would work?
Yeah, there are commercially available interseeders, or at least the row units that you can bolt onto a toolbar for that. And I would go to Dawn Equipment to find out about that. That's one vendor.
How's that spelled again? Dawn Equipment?
D-A-W-N, Dawn.
Oh, D-A-W-N, Dawn Equipment, right. Okay. Anything else before we wrap up the time with you for the day? I appreciate you taking it with us.
Yeah, thank you.
Well, thank you so much to Joe Rothermel, who's from Broadlands here, along with Stacy Zuber and the rest of the crew, including Nick Jelinski from the University of Minnesota, and our kickoff keynote speaker today, who was Jerry Costello, the director of the Illinois Department of Agriculture. We appreciate all of them being along, and to Liana Brown for helping to put this together, and to all of the folks at the University of Illinois and other places, including a whole bunch of folks from the Illinois Stewardship Alliance and others, Illinois Department of Ag, that helped to put this conservation cropping seminar forward. Our sponsors, of course, for the day, including NRCS, the Soil and Water Conservation Districts in Illinois, the Illinois Stewardship Alliance, the Illinois Sustainable Ag Partnership, the American Farmland Trust, Illinois Extension Sea Grant, and Pro-Harvest Seeds, along with Illinois Department of Agriculture. And we appreciate you taking the time as well